finishes her speech as he opens the door. She rolls over, pretends to sleep as he looks her over.
Oh, I'm going to cut you off right there. I want to see if anybody knows the name of that song and the band who made that song real famous. But anyway, welcome to Sigma Notation. And kind of sounds like a crazy, intimidating topic, but hopefully we're going to make it look like an innocent little well-trained baby cub bear. But the other name is, instead of Sigma Notation, sometimes it's called Summation Notation, and I think that's a better name. I think does a better job of describing what we're actually going to do today, is because the root word there is sum. So even though we're going to use the word sigma a lot, I want you to always replace that word with the word sum. We're just going to be adding things together today. That's what it's all about, is we're simply adding. Now, sigma comes from the Greek letter that looks like this. That's what sigma is, and mathematically, it just simply means sum. Now, to review what we talked about the other day, a sequence is simply a list of numbers in a very specific order. Okay, that's what we were focusing on, is a list of numbers in a specific order. And maybe a good example of that is maybe 1, 5, 9, let's see, 13, 17, etc., etc., etc. Now, a series is simply going to be the sum of that list of numbers that made up our sequence, okay? It's basically going to be the sum of that list. So we're going to maybe oversimplify, but I'm going to basically replace all those commas with plus signs. So now it's 1 plus 5 plus 9 plus 13 plus 17 plus dot, dot, dot. Now, with the dot, dot, dot at the end, I'm kind of getting into calculus a little bit and inferring that we have an infinite sequence or an infinite series and so forth like that. And we're never going to go all the way to infinity in our class. We're going to keep everything finite. And we're going to talk about that here in our next slide. For the series that we work with, they're always going to be very specific, and they're going to tell me exactly how many terms they want me to add up. So, for instance, if I see a big capital S with a subscript 4, what that means is they want me to add only the first 4 terms together. So S sub 4 would be the first term plus the second term plus the third term plus the fourth term, and then we would stop right there. And I'm going to put a period there to emphasize the fact that we are stopping. We are not continuing any further beyond that. Or if they said S sub 6, that means they want the sum of the first 6 terms, A sub 1 plus A sub 2 plus A sub 3, yada, 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 until we got to A sub 6. And again, stop right there. Do not go any further than A sub 6. Generally speaking, they're going to use S sub n, and that stands for the nth partial sum. And that's a term that I want you to be familiar with, the nth partial sum. Okay? But as always in math, there's kind of usually a simpler, quicker way to do that. And down here, we're going to say that a series can be represented in a condensed, more compact form called sigma notation. And that's what today's going to be all about, is how are we going to use that Greek letter to make our life a little cleaner and easier. Again, if I went a little too fast there, just hit the pause button, get that entire sentence down in your notebook so that we're complete and up to date. All right, time to jump into a few examples, and I'm guessing the first couple sigmas that you attempt to write are going to be rather crazy looking. At least mine were when I first started to write them. But anyway, here's what our first problem looks like. It says, I want you to start with n equals 1 and work your way up until you hit n equals 4. And you're going to substitute them into 3n. All right, first of all, how is this read? Okay, how do you pronounce this? How do you read it? I want everybody in the class to be on the same page and pronounce this the exact same. This is, we say, the summation. Okay, the summation from 1 to 4. From 1 to 4 of the quantity 3n. Okay, that's how we're going to pronounce this when we work in our groups, just so we're all reading it the same way, pronouncing it the same way. Basically, what we're going to do is we're going to substitute a 1 in for the n. Okay, and then we're going to work our way up in increments of 1. Okay, so our next n value is going to be a 2. Our next n value is going to be a 3, and then our final n value is going to be a 4. And the reason that I'm stopping at 4 is because that was the number up here on top of the sigma. Now all I got to do is just kind of add all these up. Let's see, that's a 3 plus a 6 plus a 9 plus a 12, a 9, 18. How about a 30? Okay. Hopefully I did that right in my head. Again, you can laugh at me tomorrow if I screwed that up. But just to review kind of what we went over here, the n equals 1 is my starting value. The n equals 4 is my last value or my ending value, and I just work my way up in increments of 1. Sometimes I like to use the terminology that this is the floor, this is the ceiling that we're using, and we're going to start on the floor, climb up to the ceiling in increments of 1, and we're just going to continuously substitute those values in for n as we go along and just continue to add them up. And that's what we've got. We've got ourselves a series. Okay, our next example, I want to emphasize we don't always have to use n's. Sometimes we can use k's. So we have the summation from 1 to 5 of the quantity k squared plus 2. All right. So again, we're going to substitute a 1 in for the k. I'm going to say 1 squared plus 2, and then I'm going to work my way up in increments of 1. So now I'm going to substitute a 2 in for k. Now I'm going to substitute a 3 in for k. Now I'm going to substitute a 4 in for k. And then last but not least, I'm going to substitute a 5 in for k. Notice the square didn't change, the plus 2 didn't change, only the value of k changes. If we clean this up a little bit, my first term's 3, my second term's a 6, my third term's an 11, my fourth term's an 18, and my fifth term there is a 27. Add those all up, I think I've got a 65. Hopefully you agree with that. I think that's hopefully pretty clear. We're just continuously substituting values in for k. Again, the square doesn't change from term to term. The plus 2 doesn't change from term to term. Now, interestingly enough, I want you to compare that to what appears to be a very similar looking series, okay? What if you took a quiz here and I gave you this? Would you assume that it's the same as the last problem? It's the summation from k equals 1 until 5 of k squared plus 2. Notice I did not put parentheses around the quantity k squared plus 2. Okay, so here's the rule. Here's the rule. If you do not see parentheses, such as this problem, you are to assume that there are only parentheses around the first term. Okay, so what's going to happen here in this one is we'd substitute the 1 for k, then you'd substitute a 2 for k, substitute a 3 for k, substitute a 4 for k, substitute a 5 for k, and then at the end of all of that, you would throw a plus 2 at the end. So that plus 2 here became this plus 2 at the end. Notice I did not add 2 along the way, and that's going to totally change the value that I get when I'm all done. So make sure you pay attention to whether there is or is not parentheses around the quantity. Okay, our third example is the summation from n equals 2 until 4 of the quantity n squared times x to the n. Now the key here is we are substituting numbers in for n only. Okay, whoops, not capital N, lowercase n. In for n only, okay? We're not substituting anything in for x. X is going to stay in x. So on the first term, I'm going to substitute a 2 in for n, and I get something that looks like that. Plus the next term, I'm going to substitute a 3 in for n. And then for that last term, I'm going to substitute a 4 in for the n values. Again, let's see, I got to get a 4 in there. I wrote n instead. The x's are staying x's. Now, if we clean this up a little bit, we're going to get 4x squared plus 9x cubed plus 16x to the 4th. And believe it or not, that's my final answer this time because these are not like terms. I cannot combine these three terms at all. I just leave them as a trinomial, and that's my final answer to that summation problem. Okay, our fourth example, we're going to say it's the summation of from m equals 1 to 4 of the quantity. Check this out. Negative 1 to the m plus 1 times the quantity m squared plus 2m. All right, now, because this is the multiplication right there, you can safely assume that this entire thing is one term. All right, so we are doing the summation of the entire thing. First thing I'm going to do is I'm going to substitute a 1 in for every single m that I see. So I've got, let's see, negative 1 raised to the 1 plus 1 power, and then I've got 1 squared plus 2 times 1. Boy, how about a boatload of parentheses there? And then I'm going to substitute a 2 in for every single m, so I've got negative 1 to the 2 plus 1 power times 2 squared plus 2 times a 2. Again, a boatload, just a boatload of parentheses. Now we're going to substitute a 3 in there. We got 3 plus 1, 3 squared plus 2 times a 3. Is that enough parentheses? Nope, I need one more. Okay, and then we've got negative 1 to the 4 plus 1 power. Then we've got 4 squared plus 2 times a 4. All right, I'm going to encourage you to try to clean this one up on your own, then come back and see if you got the same answer I did, and hopefully we agree. All right, time to see if we got the same answer. Now, let's see. Now that turns into a 2, and when you square a negative 1, you actually get a positive 1. And then all of that, 1 plus 2 is 3. 3 times positive 1. I got a 3 for that first term. Okay, I'm going to switch colors here. Now, negative 1 to the third power is a negative 1. And then inside the parentheses here, looks like I got a 4 plus a 4. That's 8. 8 times negative 1. I got a negative 8 for that second term. All right, moving on to the third term. Negative 1 to the fourth power is just a positive 1. Inside here, 9 plus 6 is 15. 15 times 1 is 15. It's simple as that. And then last but not least, negative 1 to the fifth power is negative 1. 16 plus 8 is going to be 24. So I think I've got negative 24. And if I combine these four terms, let's see. Negative 5 plus 15 is 10. 10 minus 24. How about a negative 14? I'm getting a negative 14 for my total sum. Hopefully you agree. Hopefully you got the same thing. Now after doing that last one by hand, your hands or your brain's probably fried, and I'm gonna show you kind of a shortcut on the calculator here. Now what I'm gonna do is I'm gonna do the updated version first, and I'm gonna tell you your life is gonna be significantly easier if you have the updated TI-84. If you have the TI-83, I'm gonna show you how to do it one time, and then you're on your own. Okay. But anyway, here's our fifth example. Let's say we want the summation from k equals 2 until 7 of the quantity 2k plus 2. All right, so here's what you're going to do with your calculator. First thing you're going to do is you're going to hit alpha, and then you're going to hit F2. Okay, now that F2 is right up here. You can barely see it. Oops, let me switch my pen color here. The F2 is right here on your calculator. All right, that's the menu. And once you hit the alpha F2, you should get a menu that looks like this. And on that menu, I bet you can guess which one we're going after today. Yeah, you got it. Number 2. We want to hit number 2. That's got our sigma sign. Once you hit number 2, you then should get your calculator screen should look like this. All right. And what you're going to do is, the first thing you're going to do is you're going to hit the X button. The calculator automatically moves you over. You can type in your 2. Now, the calculator did not automatically move you after you hit your 2. So then you have to hit your right arrow. And now it automatically pushes you up here where you hit your 7. And then you can hit your right arrow. And then you can type in your 2x plus 2. Now, I know the problem used k's, okay? But that's okay. On the calculator, we're going to use x's as a replacement for the k's. Once you hit enter, you should get 66. Okay, so here goes. If you wanted to do the exact same problem we just did on the TI-83 without, the version that can't be updated, here's your one shot, and it's a little more confusing, but I think you can pick this up. The first thing you're going to do is you're going to hit second, and then the stat menu, which is actually going to, once you hit second stat, it's going to take you to the list menu. Okay, you want to arrow over so you see the math option, and we want choice number 5 there that says sum. Once you hit number 5, your calculator screen should have sum and then an opening parenthesis. As soon as you get that, we're going to hit second list again, Except this time, instead of going to the math menu, we're just going to go to the ops menu, and we want choice number 5 again, sequence. So that the only good news there is that it's both times it's option number 5, first for sum and then for sequence. Now once you get that on your calculator screen, you should have sum and then sequence right now. That's what your calculator should look like. Now you've got 5, let's see, yes, 5 arguments that you have to type in. Number 1. Let me see if I can blow this picture up a little bit. Whoops, I guess. Time out. Let's see if I can erase that. Okay. Let's see if I can blow this up a little bit. Yep, there we go. Okay. Back to the pen. Now, first thing, type in the formula, or the equation, 2x plus 2. Now, comma. Comma is right above the 7 key. And then you can type in the variable x, comma, floor, comma, ceiling. And then the last one you have to have, because you're telling the calculator, I'm going to do the summation from 2 to 7, and I'm going to count by I'm going to go up in increments of 1. Okay, so that's something we haven't really talked about before, but you got to have the comma 1. Once you have all that, close the parenthesis, should hit enter, should get 66. You're going to have to be very careful, refer back to your notes, because especially like 2 months from now, it's going to be hard to remember all those 5 arguments. I wanted to do one more example on the calculator, and this is one that got us on the Regents exam not too long ago, where they threw an exponent like a cubed on the outside of that quantity, and typing this into the calculator can be a little bit challenging if you haven't done it before. And I want you to go ahead, try it on your own right now and see what you get. Okay, if you tried typing this on your calculator, I'm guessing you might have got a 20 million, let's see, 0, 0, oh, whoops, do I have my decimals off? Nope. That's 2,000,376. Okay, if you got that 2 million number, we did it wrong. Okay, and that's what I'm guessing a lot of you did if you tried it on your own. We should be getting the correct answer is 46,872, and I'm going to bring up a picture to show you exactly what your calculator screen should look like if you use the appropriate parentheses. Okay, here's the picture I wanted to show you, and what's got to happen here is we've got to include this entire quantity in its own set of special parentheses. So the calculator is going to give you that first one, and then what you've got to do is you have to manually type in that second opening parenthesis, get everything in there. Okay, get your cube in there and then close it. So there's got to be 2 sets of opening parentheses, 2 sets of closing parentheses in order to get this one right. And that's something we're going to have to practice a little bit. All right, we're going to go back and we're going to finish today's lesson similarly to the one we had yesterday when we were trying to write. Do you remember when we had to write the explicit formula for the nth term? We had to identify the pattern ourselves and come up with a formula. This is very, very similar. We're just going to throw a sigma in front of it. And they want me to kind of work backwards compared to the last couple we did and write our own sigma notation to represent the sum of this sequence, assuming that we went all the way to the first 28 terms. So what we're going to do to keep things friendly, we're usually going to start with n equals 1, and then they want me to go all the way up to 28. So I've got my floor and my ceiling. The trick is what goes here. The first term's n equals 1, the second term's n equals 2, the third term's n equals 3, and so on. And of course, the question becomes, you know, for instance, how do I turn that 3 into a 9? Or how do I turn this 4 into a 12? This is a real easy one. We're going to simply multiply the value of n by 3 to give us those terms. And then, like we said, we throw the sigma in there, add them up 1 through 28, and that's what our answer would look like if we wanted to express this series in sigma notation. All right, now this next one is about 800 times harder than the last one. But the reason I wanted to do this, there's a few special things I wanted to point out. Now, as we go to start this, just like we said in the last one, let's assume we start with 1 and we go all the way to 35. You don't have to start with 1, but I think it's going to make your job a lot easier. The next thing I want you to notice is that these signs are alternating. Okay, which means we're going to sprinkle in a -1 to the nth power in there. Anytime we have an alternating signs, we're going to have -1 to the nth power in our general formula. The other thing I want now, from here on out, it's like I said, it's an extremely challenging problem. Now, a week from now, after we talk about something called a geometric series, you'll be able to come back to this problem and make it look pretty easy. So but I'm going to just kind of cut to the chase. I'm going to propose that we use 3 times 2 to the n minus 1 power. And now you're wondering, where in the world did that come from? I don't want you to sweat about it. But what I do want you to do is to confirm that it does indeed work, okay? For instance, if I substituted a 3 into my formula, would it produce a negative 12? Okay, I'll say that again. If I substitute a 3 into my formula here, will it produce that negative 12? Okay, 2 raised to the second power is 4. 4 times the 3 is 12, and 12 times negative 1 is indeed negative 12. So I'm saying yes, it did produce it. You could also plug a 4 into my formula to see if it produced a 24. You could plug in or substitute a 5 into my formula to see if it produced a negative 48, etc., etc. But that's what I wanted you to see here. I wanted to make sure that you started with n equals 1. You put the 35 on top. And I wanted to talk about the need for that negative 1 to the nth power because it was an alternating series. Okay, now for our very last example of the night, there's something here that I think is pretty easy, and then there's something that's pretty hard. We're going to assume that we start with n equals 1 again. What's missing here is the ceiling. Compared to the last couple of problems where they said, you know, we want to use the first 28 terms or the first 35 terms, they never told me how many terms to use. But the good news is, I think we can get the formula pretty easy, okay? Do you see the pattern? Do you see the pattern? For instance, if you look at this bear right here, all you got to do is multiply the value of n by 7. And I think that same rule will work over here. So I'm going to say that it's just 7n. Now the trick becomes, how many terms am I really adding? Okay. See, the last couple of series just had ... and they left us hanging. This one actually says, I want you to go until you hit 105. So my question is, how many terms are there from 7 to 105, assuming that I wrote each one out individually? Or in other words, what we're trying to say is, what is the value of n by the time I get to 105? What term number is that? Okay, and perhaps maybe it would help us if we wrote this question out and really organized our thoughts, okay? By the time you get to 105, what term number is that? What term number is the 105, okay? In other words, is it the 10th term? Is it the 12th term? Is it the 15th term? Is it the 20th term? What term is it? Because I really don't feel like writing each term out individually. I mean, I could go 28 plus 35 plus 42 plus 49 plus 56, etc., until I hit 105. I mean, I really could do that. If you were on the Regents exam and you were stuck, you could do that by hand and work them all out until you hit the 105. But I got a shortcut. Just take the formula that you just wrote, the 7n, set it equal to 105, and solve for n. If you divide that 7 over, okay, you're going to get 15. So that means the 105 is the 15th term, and that's how many terms we want to add up total together. Again, if the last 3 were extra difficult, I don't want you to sweat it. The good news is these style of questions usually are multiple choice questions on the exam, which means we can do the plug and chug, trial and error type of strategy, which usually helps. And other than that, we're going to continue to practice and help each other out. We'll get better tomorrow. So good luck, and we'll see you then.